So thank you, Angelo and the other organizers for the invitation. So it's been a pleasure being here. So as you can see that I am going to talk about first passage processes and defects and martingales. Maybe some of you already know what are first passage processes, but again, I will just give you like a recap and try to explain what are these terms in the title. So this is the idea. Okay. So as you can see, so this is the outline of the talk. So first passage I will give a quick recap, and then I will take two very specific problems. Let's say run and tumble in discrete space-time, and then I will also consider a Brownian area functional in continuous space-time. So these are two problems in discrete and continuous, and I will tell you what is the question that I ask, how I solve these two problems, and how these defects and martingales, this can be two like techniques or tools that you can use to solve this kind of problems. Okay. So let's say what is first passage first. So if I just drop this pointer from here, you know exactly the time it will take to reach the ground, right? Unless the g value of g is changing. So, but if there is a if let's say x is a stochastic process, then I don't know exactly when it will reach the ground. And here comes like the first passage. So I will be interested in when xt, which is a stochastic process, reaches some target site x, capital T. So if you do the experiment many times, so you will get different answers. So your t, first passage time, is a stochastic variable. And then the usual question that we ask, what is the distribution, what are the moments, this is the thing. Okay. And why we are interested in this? So first passage, like it has application in many fields, like chemical reactions. Suppose there are two elements, they are moving, and you know when they come, they make a new element. So in such processes, suppose there is an animal which is moving and there is a food somewhere, when it can go and find the food for the first time. And also in finance, when a stock price like reaches your target price, this kind of thing. Okay, so this is the traditional recipe. What you do, you just search what is this called a survival probability that your x has not reached the target site within a certain time. How do you solve this problem? You put an absorbing site at your target point. When your particle reaches that point, you say, okay, my process ends, this is my time. And so you put this absorbing point, you find the propagator, you find what is the survival probability. This is in continuous, this is in discrete, and then you find the first passage time probability density from the survival probability, which is very simple formula, is a minus derivative, and then in discrete is survival at t minus 1 minus survival at t. But so I mean, very few first passage problems can be solved exactly. For just to give an example, so let's say if I take the simplest one, Brownian motion, dx dt with a random force. In technical terms, I have a Gaussian white noise here. So you can solve this problem using very method of images and also others, and you will see. So this is the like the first passage density here. If you just increase a simple one complexity, it's the next level. So you make it 2, like second derivative in x. So now it becomes non-Markovian because you need 2 time instances in the history to know what will happen in the next time instant. Okay. Now this problem took 50 years to solve. So first it was proposed by Wang and Uhlenbeck, and then it was solved by Sinai and Buchert for discrete and continuous case. Still, there are many first passage problems and people are interested in, and it is very difficult to solve. So these are the references if you just want to have a quick look. So let me just skip to what is my problem, run and tumble. So what is a run and tumble problem? So you have this let's say x dot, and then you have a dichotomous noise. So basically what is saying that your velocity is switching from a positive to negative side, like its sign, and then there is a time gap between these two, which is like drawn from an exponential distribution. So basically you have a persistence. Okay. And in continuous space-time, people have solved this problem. So you can see these references. But what we ask is this. Suppose we are moving on the lattice, and then also I have, when you have blue, so you have this positive velocity. When you will have red, you have this negative velocity. And then, as you can see here, your velocity was switching from plus to minus and then again. So here I assign to probabilities. So it's PR that I will remain with my internal state, let's say, the velocity state. There is Pj, I will jump to the, I will change my sign of the velocity. It's very simple. And then I ask the same question, what is this first passage statistics? So as you see, this is like, we have this internal state, so this is non-Markovian. So, but you can write, so you can just span your dimension, like from this 1D space and internal state in the, so now we have 2D, like this is your spatial dimension and this is the dimension of your internal velocity. Now it becomes Markovian, okay, in 2D. And then you can write the master equation, you solve the master equation, then you know the recipe, as I told you. This is the result that you get. What is this? So before, okay, let me just tell you. So as you can see here, so my velocity is positive and these are the probabilities that I remain in the positive state, and because my velocity is positive, I move in the positive direction. If I jump, I change my sign of the velocity, I move to the negative direction. Okay, so this is as simple as that. What you see on this side, so I have just added one extra parameter PL, which is a bias, adding a bias. So if PL is 1, basically you have a 0 bias. If PL is 0, you have a perfect bias. So this is the ballistic limit that you can see. Okay, so I prefer to show the solution first before I go to the methods. So this is the first passage time density, as you can see here. So you can see when we have a ballistic limit, so PL is 0, I know exactly when I will reach the target, right? So this is a delta function. So basically this will be your NT minus N0, like the distance between your starting point and your ending point. Because at every point of time, you are moving to that direction. So, and in the diffusive limit, so when PL is 1, you get this the decay, which is T to the power minus 3 over 2. Maybe you know from Brownian motion, we also see the similar kind of decay. And in the the intermediate values of P, so we have a decay like this. There is also an exponential term with this T to the power minus 3. Okay. And here what I show is the SNR, like the signal to noise ratio, the mean and the variance, the ratio of these two. So problem B, so Brownian area functional. Let's say I take a drift diffusion process. So basically this is a Brownian motion, but now I have a drift with velocity v. Okay, and I ask, okay, I will consider the area under the curve. So I have two boundaries, as you can see, this is L plus and L minus. I start my experiment. So this is one particular trajectory in one realization. So my trajectory hits one boundary. My process ends. But look, now I am interested, what was the area under the curve? Okay. So this is my variable now. If I do the experiment once again, so I will get a different trajectory. So this area under the curve, that will be like my interest now. Why? Because these are let's say one of the simplest example of Brownian area functional. Maybe people from finance, I mean, they know how this Brownian functional is important for option pricing and this kind of thing. And then we ask, okay, let's say what is this mean area? What are the relationship between L plus and L minus, the two boundaries? Okay. So this is the answer. So here what I am plotting, you see the mean area as a function of L plus and L minus. So the way to read this plot is to, for example, let's focus on the red curve first. So I'm plotting mean area with a scaling as a function of L plus. Okay. So that means my L minus, the negative boundary is fixed. I start from 0, my negative boundary is fixed, and I'm increasing L plus. Now what would happen to the mean area? So as you can see, so there is a positive drift. So we would expect that because we have a positive drift, on the average, the area should be positive, right? But we see, no, that actually there is a parameter space, a region where your area could be negative also, even if with positive drift. So the reason is that when, let's say, this is my 0, my L minus is fixed, and I'm increasing L plus. So when L plus is small, so you still have some trajectories that goes below and then come to the positive side. So those trajectories gives you a negative contribution. On the other hand, if you focus on the blue curve, so again here what I'm doing, this is my 0, I fixed L plus and I'm increasing L minus. Okay? And you can see because I have a positive bias, so eventually, more or less when my L minus is very big, basically all the trajectories will come and hit the positive boundary. So at some point, the trajectories will exhaust and then I will get this saturation value here in the area. Okay. So these are the results. Now let me just tell you how to solve these problems. Okay. So defect. So first of all, what is this defect? So I will just quickly go through. So suppose you have a like a lattice here, and you have solved this problem. So you know what are the propagators. Now I come and I just make one side defective. So what I do, I will just change the probabilities. And then I ask, what is the solution of this problem? Okay. Now, I mean, do you need to solve the problem from scratch? The answer is no. If you know the solution of this problem, you know exactly the solution of this problem in terms of the solution of this problem. So this is the defect technique. So this is a defect, and you know how to write the solution of this in terms of this. Okay. Now you can change these probabilities like in various ways. You can mimic various boundaries or boundary condition reflecting and periodic. But when let's say, because we are talking about first passage, we will make this absorption boundary, absorbing boundary. Okay. So what you do? So you just write your master equation in the defect-free case, and then you write your master equation with the defect, where you see there is a leakage in probability. Basically, it tells when you are on the defective side, there is a leakage in probability. Okay. But still, what is important is that you still have a linear master equation. So you can just write the solution of this problem as a defect-free propagator, and the propagator convoluted in space and time. Okay. So you just write the defective solution. Sorry for a little bit of mathematics. In terms of the defect with the propagator with defect, in terms of this defect free propagator, you put it in your master equation, you go to the Z domain, you use the linearity of master equation, and you have all this solution, like what is the defective propagator, what is the survival probability, what is the first passage time probability, whatever you have on your right hand side. So this is exactly in terms of the defect free propagator. So you don't need to solve, like if you know the defect-free solution, you know exactly what will happen on your left. Moreover, in this sum, so you will get the splitting probability. So each term, let's say you have two defects. So then in this sum you will have two terms. The first term will tell you will hit one boundary and not the other. And the second term will tell you will hit the other boundary, not the first one. So this gives you the splitting probability. Okay. And now we just solve our problem. This is the defect-free problem. Okay, I'll just skip this one. And then you add defects here. You use that technique, and you have the solution. This is your first passage time density in generating function. This is the mean. You can see if you have a ballistic limit, this is exactly nt minus n0. Yeah. And if you have a zero bias, this diverges, as we know. So I have already shown you this result. And if you just plot the mean square displacement, you can see there is a kind of like anomaly here. So you have a super diffusive regime from like when you change the PL here. So very quickly, let me go to the second one, Martingales. So first of all, let me give you a definition of Martingales. People are using Martingales in finance, in mathematics a lot, but in physics, maybe we are not, so we can exploit it a little bit more. So what is a martingale? So you see, it is defined in terms of a conditional average. So it tells you MT, let's say you consider any stochastic process MT defined on another stochastic process X. So given the information of X from 0 to S, if I take an average of M, and if M satisfies this condition, this is a martingale. Just to give you an example, let's consider Brownian motion. So I give you the trajectory from x0 to xs, and then I ask what is the average of xt at a later time. Okay. So what I will do, let's say I will just draw many trajectories here, and if I take the average here, what I will get? I will get xs, right? So xt is a martingale with itself. Okay. Now what I will do, so and there are in mathematics, I mean there are many theorems that mathematicians have proved for this thing. I will take one particular theorem that is called Dup's theorem. So what Dup's theorem tells you, you consider any stopping time. So stopping time means you have to set a criteria when your process ends. Okay. So you just like you take the stochastic process xt, and then when it satisfies some criteria that you specify, then your process ends, and this is the stopping time. In our case, it could be the first passage time. We know when we hit these boundaries, our process ends. So I will just apply this Dup's theorem, which tells expected value at stopping time equals expected value at the initial time. So this is a theorem, you can prove it. Now let's see what happens, the magic. So I will apply this to our problem. Remember the area function. So, but I have the deep diffusion process because I have V. But I know that if I have a drift, it is not a martingale, right? So on the average, so for example, let's say, I'm sorry. Yeah. So this condition will be violated because if I have a drift, so on the average, I will not, if I do the averaging here, I will not get excess. If I have positive drift, maybe I will get something, I will do the average, I will get something else, like more than excess. So first we need to just consider, create like martingale, and if there is a drift, if the drift is positive, it is submartingale, if it is negative, it is supermartingale. So first we need to create a martingale. There are ways to create a martingale if you have a process with drift. One example is this Dolian's date family. So you take, BT is your winner process, the usual Brownian process, and this like Dolian's family, it tells you this stochastic exponential is a martingale. Just trust me, this is a martingale. Now let's see what we can do like with it. So I know my x is submartingale because I have drift. So I just write x in terms of this BT, I put it here, and I know this is a martingale. So for me now this is a martingale. Now you see the magic. I know this is a martingale. I apply the Dup's theorem, which is a very simple theorem. I put it here, and as soon as I put it here, I see this is a generating function of the first passage problem. But you see here, let's say this t is the stopping time, and you just consider all of this as your Laplace variable, and you have the generating function in one line. Okay, and which we know this is the solution here from the Brownian particle. And then there is also another family which is more general. You take any Markovian process x, and you take any real valued like smooth function g, which is the function of x and t, and this is a martingale. Okay, by definition you can prove it. What we do, we know where this L is the L dagger is the Fokker-Planck generator of your x. In our case, in the drift diffusion process, we know what is the Fokker-Planck generator. We just apply it here, and we get this. So this is our martingale. You see, but still we have a freedom to choose the form of g. Now I take a specific form of g. You see the simplest, x squared. I put it there. This is a martingale. I apply Dup's theorem, and voila, I have the mean area at the stopping time in one line. Okay, so, and this is the scaling form of this area, and this is the plot that I showed you before, the mean area. And remember that here we have a positive velocity, and similarly If you consider negative velocity, you still have some parameter region where your mean area is positive. So what it tells you, if there is a losing game where you know you have a negative drift, you will lose your fortune. If you make your strategy not on X but on area, you know there is a parameter region where you can make the losing game in your favor, so winning it. And so that's all. So take home message. So I described two methods to tackle first passage problems, defects and martingale, and I show how we can use this to solve non-Markovian and Markovian dynamics and defects, and both of them give you exact analytical solutions. This is handy basically when there are interacting workers, and martingales is very elegant, but first you need to construct a martingale from your dynamics. And thank you. These are the references.
In your model, you use it when you have the jump from one side to another side with the change of velocity of the time distribution, the exponential distribution. No?
Yeah.
What change in your result if you, for instance, use different distribution of probability for the duration with the same velocity?
But okay, so this is the thing that you are, let's say, if I change this probability, this is a problem in continuous space-time you are talking. Yeah. But here what I told you is discrete. In discrete, so it will only change your PR and PJ, right? So these are the two probabilities that you will remain with the same state, PJ you jump to the other state. So because of these two parameters in discrete, so we know exactly the same formalism, what we have here, and you give the same answer.
But not depending on
because in discrete, it depends only on PR and PJ.
Thank you, very interesting talk. Can you say some more about the application of real data, like how long should be a real-time series, the applicability, any, let's say, things to take into account? If I have, let's say, a physiological time series and I'd like to apply the methodology.
So let's say, okay, I suppose your question is regarding first passage, right?
Yeah.
So basically, you need to say what is your target. So to answer all first passage problems, you first need to say, okay, this is what is my target, like what I am going to do. So if you know what is your target, then you have some kind of understanding, right? So for example, let's say, just take the simple example of Brownian motion. Okay, so you know your mean square displacement, how it increases with d, with the diffusive way, right? So you have some kind of understanding when you will reach a target, right? So
yeah, but then let's say the minimum length required, how many samples? It's like 1,000, 5,000, 10,000.
Okay, so you are saying you have a finite time series.
A real data that I measure from something, a real time series.
And you don't know about the dynamics, right?
I might hypothesize what's the dynamics let's say behind.
Okay, so let's say, okay, suppose I start from some x0. My target is, let's say, at very far, and I have a very small time series. Of course, I will not hit the target. But if you know the dynamics, or if you hypothesize the dynamics, maybe you have some kind of understanding, as I said in Brownian motion, how long the time series should be, that you know, okay, at least you hit the target from those.
Thank you very much.
Okay. We thank again Lars.
Thank you.